Welcome to the first video of this series. This series is designed for people with a limited knowledge of algebra and mathematics in general. It should be accessible to all levels, from beginner to advanced mathematicians. By the end of this series, you should have developed a strong intuition for the foundations of mathematics, which are used across a wide variety of disciplines. So I chose to begin with number systems as chapter 1, since number systems pretty much encapsulates everything we're going to be doing in the next while. So number systems are just sets of numbers, and a set is a well-defined collection of objects. So an example of a well-defined set would be the set of all whole numbers between 1 and 10, whereas the set of good musicians isn't a well-defined set, since it's a subjective opinion. Now we will be learning a lot more about sets in a future video, so I wouldn't get too worried about the definitions at the moment. So here we've got the set of natural numbers, which is just a set containing all of the positive whole numbers which are greater than 0. So positive numbers are just numbers that are greater than 0, and whole numbers are non-decimal numbers, they're whole. So I can write a couple of different numbers down. So we've got -5, -3, 1, 7, and 50. Now 1, 7, and 50 are all positive whole numbers, and -5 and -3 are negative whole numbers. -5 and -3, just like any negative numbers, are not elements of the set of natural numbers. The set of natural numbers is denoted by the capital N, and the curly brackets tell us that we are talking about a set of elements. An example of an element of this set would be the number 5, the number 3, the number 1, the number 5,000, the number 1,000,000, and so on. The ellipsis, or the 3 dots at the end of the set, tells us that the set continues in the same fashion all the way until infinity. This is also indicated in the number line by the arrow pointing towards the right. Number lines are very effective at representing different sets of numbers. You can see here that this number line represents all of the natural numbers from 1 to infinity. Now, the reason that I said 1 to infinity and not 1 to 6 is because the arrow at the end of the number line stretches all the way out to infinity. You might notice when taking a look at this number line that non-whole numbers are not plotted. For example, 1.5 is not plotted on this number line. That is because decimals are not elements of the set of natural numbers. Okay, so now that we know what the natural numbers are, we can start actually working with these numbers. So taking a look at the numbers 18 and 45, it is easily shown that these numbers are made up of different products of numbers. For example, taking a look at the number 18, I can make 18 by multiplying 1 by 18, 2 by 9, or 3 by 6. In the same way, I can make the number 45 by multiplying 1 by 45, 3 by 15, or 5 by 9. Since these pairs of numbers make up 18 and 45, we can say that they are factors or divisors of 18 and 45. A factor is a number that divides another number with no remainder. So you can see if you divided 18 by 1, you would get 18. If you divided 18 by 2, you would get 9. And if you divided 18 by 3, you would get 6. Some numbers have common factors, which are just factors that are common to both numbers. So for example, 18 and 45 have the common factors 1, 3, and 9, because they can all be divided into 18 and 45, leaving no remainder. The highest common factor of 18 and 45 is 9, since 9 is the largest whole number which can be divided into 18 and 45, leaving no remainder. So this is the end of the first part of number systems. In this section, we've covered natural numbers and factors or divisors. In the next section, we will look into integers, multiplication and division of two integers, and the order of operations. The set of integers contains all of the positive and negative whole numbers, including 0. The set of integers is denoted by the letter Z. Since the set of integers contains all of the positive and negative whole numbers, we use an ellipsis on either side of the curly brackets to tell us that the set continues to infinity. This can also be denoted by placing an arrow at each end of a number line. Now that we have defined the set of integers, we can now learn about multiplication and division of two integers. The results of multiplying and dividing numbers vary depending on whether a number has a positive or a negative sign. When you multiply or divide two numbers with the same sign, you get a positive result. For example, if you divide minus 15 by minus 5, you end up with plus 3. This is the same as saying 3. Another example would be multiplying minus 3 by minus 5. Here we get plus 15. This is the same as saying 15. An obvious result, which I won't write down, is multiplying or dividing two positive numbers. Since their signs are the same, you get a positive result. When you multiply or divide two numbers with different signs, you get a negative result. For example, dividing minus 15 by 5 gives minus 3. The same is true if the minus is swapped between the numbers. For example, dividing 15 by minus 5 gives you minus 3. And again, by multiplying minus 3 by 5, or 3 by minus 5, we get minus 15 as a result. So to conclude this section, we can say that multiplying or dividing with the same signs gives us positive results, and multiplying or dividing with different signs give us negative results. Here is a Venn diagram representing what we have looked at so far. Venn diagrams are very useful in illustrating how different sets interact with one another. In the previous video, we had a look at the natural numbers, which is shown here by the blue circle. The set of integers is shown here with the yellow circle. The set of integers contains every single element of the set of natural numbers. This has been shown in the Venn diagram by placing the ring representing the set of natural numbers inside the ring representing the set of integers. We will cover the sets of rational, irrational, and real numbers in future videos. Now it is time to take a look at the order of operations. The order of operations tells us in which order different operations should be applied to a sum. Operations are just mathematical processes. For example, multiplication, division, addition, or subtraction of numbers. The order of operations can be memorized by using the acronym BEMDAS, which stands for brackets, exponents, multiplication, division, addition, and subtraction. Whenever we are dealing with more complex sums, we can use the order of operations to apply each operation in the correct order. Here is an example of a sum in which we would need to use the order of operations. In this example, we have to deal with the addition and the division operators. By taking a look at the acronym, it can be said that division is the first operator that should be used within this sum. So to begin, we must divide 32 by 2, which leaves us with 16. Replacing the original sum with our answer, we are left with 9 plus 16. Now, the only operator that is left is addition. By applying the addition operator, we get 9 plus 16 is equal to 25, which is our answer. Here is another example where the order of operations is necessary in finding the correct solution. It is easy to see that the brackets is the first operation that we must calculate. By calculating what's inside the brackets, we get 3 plus 3 is equal to 6. Replacing this in our original sum, we end up with 5 multiplied by 4 minus 18 divided by 6. We don't have any exponents in this sum, so the next on our list is multiplication. Multiplying 5 by 4, we get 20. Now we can update our sum. We do this by replacing 5 multiplied by 4 by 20. Here we have 20 minus 18 divided by 6. The next operator on our list is the division operator. Since division is present in our sum, we must use the division operator to calculate 18 divided by 6. Here we get 18 divided by 6 is equal to 3. Replacing 18 divided by 6 with 3 in our sum, we find ourselves left with 20 minus 3. The only thing left for us to do is subtraction. By calculating 20 minus 3, we end up with 17. The final example uses every operator except addition. By the order of operations, we must calculate the brackets first, and in this example, we have two sets of brackets to deal with. By calculating the contents of each bracket, we get 5 minus 3 is equal to 2, and 6 minus 2 is equal to 4. Now we can update our original sum. Here we have 4 multiplied by 2 squared divided by 4. The next operation on our list is calculating the exponent. An exponent is a power that a number is raised to. So in this example, 2 is raised to the second power. This means we multiply 2 by itself, or in other words, we take the square of 2. More information on exponents will be found in a future video on a chapter named Indices. Taking the square of 2, we get 4. This is because 2 multiplied by 2 is equal to 4. Now we can replace 2 squared by 4 in our original sum. Next on our list is multiplication. Instead of using a multiplication sign, here the number 4 beside the bracket indicates that we are multiplying 4 by 4. Any number placed beside a bracket means that the number is being multiplied by everything inside that bracket. So in this example we have 4 multiplied by 4 because 4 is inside the bracket. In the case of 2 brackets beside one another, everything inside each bracket is multiplied by each other. So multiplying 4 by 4, we get 16. Updating our original sum, we can replace 4 multiplied by 4 by 16. Now, the division operator is the only one remaining. So calculating 16 divided by 4, we get 4. So before the end of the video, I just wanted to make a quick note about exponents. In the previous example, we seen that 2 squared is equal to 2 multiplied by 2, which is equal to 4. Recall here that 2 brackets beside one another means multiplication. Now squaring minus 2, we see that it gives the same answer. This is because, if you remember back to the very beginning of the video, we said that 2 numbers being multiplied by each other with the same sign gives us a positive result. One thing to be wary about is where the negative sign is when squaring a number. Brackets are not always a necessity when writing a number to the power of another number. But in this case, on the third line, you can see that if a negative is placed outside of the bracket, we end up with minus 4 instead of 4. This is because the number being squared is 2, not negative 2. So in this case, the square is being applied to 2. So we get 2 multiplied by 2 is 4. And then the minus is applied to the 4. So our answer is minus 4. As a result, we can say that the first and second lines are equal, but they are both not equal to the third line. A rational number is a number that can be expressed as a quotient or a fraction. You can see that the set of rational numbers is denoted by the letter Q. Here it is written that the set of all rational numbers Q is equal to the set of all numbers P divided by all numbers Q, where the numbers P and Q are elements of the set of integers, and Q is not equal to 0. So what this means is that the set of rational numbers is comprised of all of the numbers which can be made by dividing one integer P by another integer Q, where Q cannot be equal to 0. We call these types of numbers fractions, with one number being divided by another. Fractions have a numerator and a denominator. The numerator, P, is just a number at the top of the fraction. The denominator, Q, is the number at the bottom of the fraction. Now, if you take 2 as the numerator and 1 as the denominator, 2 divided by 1 is equal to 2. The number 2 is not a fraction, but it's still an element of the set of rational numbers. The reason that the number 2 is included in the set of rational numbers is because the set of rational numbers contains all of the integers and natural numbers. The number 2 can still be written as 2 divided by 1, but we simplify that to 2. And for this reason we can say that not all rational numbers are fractions. Here is an example of a rational number. The fraction 1/2 is also equal to 2/4, or 3/6, or 4/8, and so on. Another example would be 1/3, which is equal to 2/6, 3/9, 4/16, and so on. We call these kind of fractions equivalent fractions. Now that we have defined what fractions are, we can start looking into addition and subtraction of fractions. When we want to add or subtract fractions, we must add or subtract the numerators from each other. But in order to do this correctly, the fractions both must have a common denominator. So what is meant by this is the denominator of both fractions has to be equal. Recall that the denominator is just the number on the bottom of the fraction. So here we can begin with an example. So suppose we want to add 1/2 and 3/5. Taken from what we said previously, we must find a common denominator between both of these fractions. An easy way to do this would be as follows. Here we take 1/2 and we multiply it by the denominator of the other fraction divided by itself. Then we take 3/5 and multiply it by the denominator of the other fraction divided by itself. So we get 1/2 multiplied by 5/5 and 3/5 multiplied by 2/2. Now we can see that the results have a common denominator, a denominator which is common to both. In this case, the common denominator is 10. Now that we have a common denominator, we must add the numerators of each fraction. Here we get 5/10 plus 6/10 is equal to 11/10. This is like saying if I had 2 pizzas with 10 slices each, and I took 5 slices from one and took 6 slices from another, I would have 11 slices in total. Now I have 11 slices of pizza, whereas the box originally only had 10. Here is another example where we want to take 2/3 from 1/4. The denominator of 2/3 is 3. So we take 3 divided by itself and multiply it by 1/4. The denominator of 1/4 is 4. So we take 2/3 and multiply it by 4 divided by itself. Here we get 3/12 and 8/12. So 12 is our common denominator. Here we can see that subtracting 3 minus 8, we get -5. So 3/12 minus 8/12 is equal to -5/12. Multiplication of two fractions is slightly easier. So for this, all you have to do is take the numerator of one fraction and multiply it by the numerator of the other, and do the same with the denominator. Here's an example. Recall that in the previous video, I said that 2 brackets beside each other means multiplication. You can see that this is equal to 1 multiplied by 2 and 2 multiplied by 7. 1 multiplied by 2 is equal to 2, and 2 multiplied by 7 is equal to 14. So our new fraction is 2 divided by 14, or 2/14. 2/14 can be simplified to its equivalent fraction 1/7 by dividing the numerator and the denominator by 2. So here we have 2 divided by 2 is equal to 1, and 14 divided by 2 is equal to 7. In the next example, we have 3/2 being multiplied by 7/2. Again, for multiplication of two fractions, we multiply the numerator by the numerator and the denominator by the denominator. Here we've got 3 multiplied by 7 divided by 2 multiplied by 2. 3 multiplied by 7 is equal to 21, and 2 multiplied by 2 is equal to 4. Now this fraction cannot be simplified anymore, since 4 cannot divide into 21 evenly without leaving a remainder. When dividing two fractions, you must multiply the numerator of the first fraction by the denominator of the second, and the denominator of the first fraction by the numerator of the second. This is the same as saying turning the second fraction upside down and multiplying. Here in our example, we have 1/2 divided by 2/7. So what we're going to do is we're going to turn the second fraction upside down, and we're going to change the division sign to multiplication. Now we have 1/2 multiplied by 7/2. This is equal to 7/4. Let's say you wanted to divide 9/2 by 6/4. Now 6/4 has an equivalent fraction 3/2, but I'm going to leave it as 6/4 in this example. If you wanted to make your life a little bit easier, you could simplify 6/4 by dividing the numerator and the denominator by 2. So 6 divided by 2 would be 3, and 4 divided by 2 would be 2. So 6/4 is equal to 3/2. So just like last time, we're going to take the second fraction and we're going to turn it upside down. And we're also going to change the division sign to a multiplication sign. So the last thing left for us to do is to multiply the two numerators and the two denominators together. 9 multiplied by 4 is 36, and 2 multiplied by 6 is 12. So our answer is 36 over 12. Now, since we haven't simplified 6 over 4 into its equivalent fraction 3 over 2, we can now simplify 36 over 12 by dividing the numerator and the denominator by 12. 36 divided by 12 is 3, and 12 divided by 12 is 1. So we're left with 3 over 1, or more simply, 3. Recall back to my video on natural numbers, where I talked about highest common factors. 12 is the highest common factor to both 36 and 12. So that's why when we divide the numerator and the denominator of a fraction by the highest common factor, we get the fraction in its simplest form, and in this case, it's just 3. The reason that we didn't simplify 7 over 4 in the first example is because the highest common factor to both 7 and 4 is 1, and dividing by 1 does not change the fraction. So any time that you want to simplify a fraction, you just divide the numerator and the denominator by the highest common factor. And I did this a couple of times during this video. It is good practice to use simplified fractions since they are easier to interpret, and it's very easy to keep track of what you are doing within your sum. Here is an updated version of the Venn diagram that we took a look at in the last video. You can see that the set of integers and natural numbers are inside the set of rational numbers. Irrational numbers are numbers that cannot be expressed as simple fractions. What does this mean exactly? Well, in the previous video, we took a look at rational numbers and fractions. It was easy to say that, for example, 0.5 is equal to 1 divided by 2, or 1/2. So 0.5 would be a rational number, because it can easily be written as 1 divided by 2, which is a number expressed as a simple fraction. Now we are dealing with numbers which cannot be expressed as simple fractions, and I have 2 examples shown here. The first example is the square root of 3, and the second example is the number pi. As decimals, these 2 numbers never repeat themselves or terminate, and therefore they cannot be written as one integer divided by another. So it can be said that rational numbers have a ratio, since they can be written as the ratio of 2 integers, whereas irrational numbers have no ratio. The set of irrational numbers is denoted by r/q. What this tells us is that the set of irrational numbers contains all of the real numbers which are not present in the set of rational numbers. If you recall from the previous video, we said that the set of rational numbers contains all of the numbers which can be made by ratios of 2 integers, where the denominator cannot be equal to 0. So therefore, any number which cannot be made by ratios of 2 integers, where the denominator is not equal to 0, is an irrational number. This can be shown in the Venn diagram, since the set of irrational numbers is separate to the sets of rational numbers, integers, and natural numbers. We can see that the set of real numbers is made up of the sets of rational and irrational numbers, and the sets of integers and natural numbers are subsets of the set of rational numbers. The set of real numbers is the union of the sets of both rational and irrational numbers. The set of real numbers represents all of the decimals and whole numbers from negative infinity to positive infinity. So taking a look at the Venn diagram again, we can see that the sets of both rational and irrational numbers are subsets of the set of real numbers, and the sets of integers and natural numbers are subsets of the set of rational numbers. This is the end of the chapter on number systems. In this chapter we covered natural numbers, integers, the order of operations, rational numbers, and then irrational and real numbers. Thanks for watching, and I'll see you in the next video.